Give us a Socratic look at logical weaknesses in modern pure mathematics.
Thanks, Dennis. Well, thank you all for coming. So I hope we can have a fun hour investigating some perhaps difficult issues. So in my opinion, modern pure mathematics has actually a fair number of serious logical problems. The gap between what us pure mathematicians are claiming and what the computers can actually do is now increasingly becoming so obvious that I don't think it's really going to be supportable for much longer. So it's really time that we had a closer look at some of the problems. That's what I hope to do today. I'd like to phrase this in a little bit of a Socratic way, so I'm hoping to invite you to answer some questions. So I'm going to be posing some questions. I hope that you'll be able to answer yes or no, so make some decisions about which way you lean on various points of view. And don't be afraid if you're the only one or just a few who go in one direction. Okay, so what is the overall problem? So largely speaking, the problems really have a major historical basis, and they really revolve around the nature of the continuum and attendant problems of analysis. Okay? So these are problems that in some sense go back to the time of the 17th century. There were already problems with the calculus there, and people tried to patch them up in various ways. And by the end of the 19th century, sort of a solution had been found, but in fact I think that solution is actually quite unsatisfactory. The 20th century went on to create a sort of a set theory in order to buttress up analysis, but I don't think that works either. And it's time that we had a good look at these things. So these are topics that are, in fact, not studied as much by undergraduates as they ought to be. They really are central questions that we'll be raising here. So the starting point is the nature of the continuum. So the discrete aspect of mathematics is relatively simple, right? We have these numbers that we use to count. 1, 2, 3, 4. The continuum is much more problematic aspect. So we like to draw a line like this. We like to imagine that we're going like this and that we're doing something that's continuous. But when we actually inquire to the mathematical basis of that, it's somewhat more problematic. It's a lot more problematic. So the really fundamental question in mathematics historically has been, how does one model the continuum correctly? This is very, very subtle and difficult problem. Now, you will all think that we've solved this problem, that the problem is contained in the so-called theory of real numbers. So I hope to show you today that that's actually far from being the case. Okay, so of course we can have a physical point of view, but we all know that if we blow this thing up, that and look at it at a small scale, quantum mechanical effects and so on take place. So our physical intuition is not really a good guide. The Euclidean era, in the time of ancient Greeks, they realized that one way of approaching this was to use constructions. So we can certainly divide this thing into, say, 2 and create a midpoint, which these days we like to ascribe numbers to these geometrical things, so we can make that point 1/2. We could also subdivide this equally into 3 pieces, giving us points 1/3 and 2/3. Or we could subdivide this thing here into 5 pieces, and so on. So the essence of the Greek point of view was one of repeated subdivisions to try to understand what's really going on. Now if we take some little subinterval, say AB, we can blow that subinterval up and look at it in a more magnified way. And one of the things that we start to realize is that the problem of understanding this subinterval is really the same problem as the original interval. In other words, if we have some point lambda here between 0 and 1, we can associate to that point lambda the convex combination 1 minus lambda A plus lambda B, which has the same relation in here as the lambda did up there. And so there's a correspondence, a complete correspondence between rational points that are accessible to the Greeks in this small subinterval as there are in the original subinterval. So we're not really making things simpler by subdividing. The same problem is always looming, no matter how far we subdivide it. But one thing that does happen is that the numbers involved become bigger, in the sense that we're talking about fractions with bigger and bigger numerators and denominators. So how do we actually get at just the rational numbers in 0, 1? That's a sort of initial question. And a very interesting answer to that, probably the best answer that we have, was discovered in around 1860 by a German number theorist and a French clockmaker. So Moritz Stern and Achilles Broco discovered something which is now called the Broco tree. It's a lovely thing. Okay, so here's what it is. We start with 0 and 1 up at the top, and we perform the mediant operation. So mediant is where you add a plus b, a over b plus c over b. That is by definition a plus c over b plus d. Sort of a grade 1 way of adding fractions. Okay, so to take the median of these two, we get 1/2. And then the rule is that at every stage, it's a binary tree, so at every stage, what we do if we want to know this thing here is we take the median of the two things which are most immediately above it to the right and left. So taking the median here, we get 2 over 3. The median here, we get 1 over 3. And then this place here, we would take the median of these two, which would be 2 over 5. Median here is 1 over 4, and so on like this. We can keep doing this. For example, if we went down here, the next one to the right would be, we'd have to take the median between this one and the one that's directly above it to the right, which is this one up here. So that would be 4/9. While the one to the other side would be the median of these two, which would be 5/12. Okay, so what ends up happening is that every fraction between 0 and 1 ends up in this tree exactly in one place. And where it appears, it does so in reduced form. And moreover, if you read from left to right, they're all in the correct position. So if you want to know what the interval 0, 1 looks like, this is the best answer that we have. Now notice that, okay, I've gone down to a certain stage. We could, of course, keep on going down, and the tree would become bigger and bigger in the sense that the fractions involved get bigger and bigger denominators. It's a binary tree, so in fact if we associate, say, left and right, then we can ultimately denote position here by the sequence left, right, right, right. It's intimately connected with the theory of continued fractions. It's also a nice thing for linear algebra people. If you want to find matrices of determinant 1, what you do is you look at a pair of adjacent elements in this sequence and you just put them in a matrix and you automatically have something of determinant 1. So there's a natural connection with SL2R, in fact, hyperbolic geometry, and lots of things that are connected with this tree. Okay, so now I want to come to the first question that I want to ask you. Okay, so it's obvious that I can continue this at least for a while. And my first question is this an infinite tree? Okay, so before you automatically answer yes, let me pose the no side. Okay, so as I keep going, I'm going to get bigger and bigger numbers. Eventually, the numbers that I get are going to be too big to fit on my hard drive. Eventually, the numbers that I get are going to be too big to fit on a hard drive, which is the size of the galaxy. That's the way things work. Okay? And so eventually, I'm actually not going to get that far, but theoretically, we can get to numbers where all the elements in the row are so big that none of the numerators or denominators will fit on a hard drive, which is the size of the galaxy. At that point, we're starting to sort of scratch our heads and say, well, is this really, in what sense does this thing really exist? But theoretically, we can still imagine further, and we can go imagine a little bit further to the stage where at this point, none of the numerators or denominators fit into the known universe, no matter how you represent them. So no matter how, what representational system you pick, all of these numbers here are so big that they don't fit into the known universe. That will happen, theoretically, right? But when we write down the top bunch of rows like this, we're just looking at some very obscure, really top corner of this thing. We're not really getting at the essential aspect of things. The essential aspect is down here, and that's all in complete darkness. That's inaccessible to us. So I'd like to propose that it's proper for us to look at this thing with some skepticism, and we should say, well, it's pretty certain up to here, and then it starts getting murky, and then eventually we lose track of it altogether. we're not able to claim that this is an infinite tree. Okay, so I'm not sure if I've convinced you. It's all right if I haven't convinced you. So let's take a vote. All right, take a position. Is this an infinite tree or not? We ready to take a position? How many say yes, it is an infinite tree? How many say no, it is not an infinite tree? A few people. Ah, great. So we don't all have to be in agreement. Okay? The important thing is that we're putting the questions on the table and letting people think about them. That's what I want to do. Okay, so let's do something a lot simpler. So this is getting rather complicated. There's another way of thinking about the interval 0, 1 that goes back to a Belgian, Flemish inventor, physicist, mathematician named Simon Stebbin in the 1500s. And he was the one who introduced the idea of decimal arithmetic. And he said, okay, what you really want to do is you want to forget about dividing into all kinds of weird fractions. Always divide by 10. So he was the original proponent of decimal systems in Europe. So Stebbin said, we divide by 10, so you do 0.1, 0.2, etc. like this. And then if you want to go further, you just take whatever interval you want, and of course you divide that up into decimals, 10 of them. So you have 0.21, 0.22, and so on. So by subdividing by tens, we can create decimals. Things like 3.1596. And we can do arithmetic with decimals. In fact, he showed how to basically do addition and multiplication with decimals, finite decimals, by just basically doing integer arithmetic and keeping track additionally of the decimal point. And you'll be all familiar with that. Stebbin did more, however, though. He also used this to do something that was very profound, and it's usually now attributed to Weierstrass, which is basically, he showed why the intermediate value theorem works. Okay. So the intermediate value theorem, let me use that, describe that in the context of a very important problem. So here is a rectangle of size 2 and 1, and I'm interested in the question of whether this diagonal has a length. That's the question. That's my second question to you. Okay, does this diagonal have a length? And he goes, of course it does. What are you talking about? All segments have lengths. But let me try to convince you a little bit otherwise. Okay, so if this had a length x, then x would satisfy x squared equals 2 squared plus 1 squared, so x squared equals 5. That means we have to find a square root of 5. The ancient Greeks realized that there was no square root of 5, in the sense that there was not a rational square root of 5. But Stebbin said, okay, well, we can approach this problem the following way. Let us graph the curve y equals x squared. And okay, it has the value 1. Here it has the value 4. A little while later it has the value 9. And what we're interested in is where it has the value 5. That's what the equation we're trying to solve. We're trying to find this point here. Okay, so this is a very important problem, finding the square roots, that goes back to the Babylonians. The Babylonians had a way of calculating square roots, which turns out to be equivalent to Newton's approach using calculus. And then the Hindus also had a more sophisticated approach to finding square roots, which used to be taught in schools, but is no longer. Stebbin proposed another way of approaching this problem, which is so general that it applies to solve almost every equation you can possibly imagine if you sort of think of things in the right way. He said what we do is we just bracket. So we can see clearly that 2 squared is 4, and 3 squared is 9. These bracket the value that we're interested in. So the answer has to be between 2 and 3. Great. So we divide this up into 10 pieces. We have then 2.1, 2.2, etc. And we just evaluate the same function at those intermediate 10 points and see whether the values are bigger or less than our value 5. If we do that, we find that 2.2 is a little bit less, and 2.3 is a little bit more. So the square root of 5, should it exist, is going to be 2.2 and then something else. And then just repeat. Now we know it's somewhere between 2.2 and 2.3. Divide it up into 10. Do a search, maybe do a binary kind of search to make it a little more efficient. Find the unique interval in here such that that function brackets around 5. And then you keep on creating more and more decimals this way. So what you get is 2.2, 3, 6, 0, 6, 7, 9, 7, 6, 7, 9, 7, 7, 4, 9, 9, 7, 8, 9, 6, 9, 6, 4, 0, 9, 1. And you can keep going. At no stage are we doing anything appreciably different than we were before. It's the same kind of problem at every stage, except that the numbers that we're working with are a little bit bigger and more cumbersome to work with. Okay, so before we come to the square root of 5 question, I still have to ask you that question. So let me ask you the following question. Suppose we follow step. We have a process that we have to do. At each stage, we have to make this calculation. So I want to ask you, can we finish that calculation? Can we finish that calculation? Yes or no? May I see the yeses? May I see the no's? Okay, good. Now I'd like to ask a secondary question. If we cannot actually complete the process, are we allowed, or are we going to allow ourselves to write a certain squiggle, say, to represent the completion of that process? Is that allowed? Of course, that's what we do, right? Except the squiggle doesn't look like this. The squiggle looks like this. This is the squiggle that we write that represents in our mind the idea of completing this process, which, well, in fact, we can't finish. So the question is, are we really allowed to do this and to introduce this as a new object in mathematics? I'm going to say, yes, we're allowed to do this. I'm going to say, no, we're not allowed to do this. Okay. I notice that there's a bit of tension, though, between your last two answers, right? There's a little bit of tension there. Okay, so now we move to the real issue, which is the issue of real numbers. Okay, so in particular, numbers that go beyond fractions or beyond finite decimals. So the real numbers have lots of different ways of being thought about, and the standard, and probably the most familiar one, is as an infinite decimal. But there are also Cauchy sequences or equivalence classes of Cauchy sequences. There are things called Dedekind cuts. And in fact, there are also paths in the Stern-Brokow tree. That's actually the most beautiful way of thinking about a real number, is as an infinite path down this Stern-Brokow tree. Okay, but the more familiar one is as an infinite decimal, and that's the one that I want to talk about today. So in my opinion, the theory of real numbers is highly problematic. And you don't agree with me, but all your computers agree with me. So I have lots of powerful friends. They're called computers. Okay, so what do I and my computers believe? I and my computer and our computers believe that what we really have is floating point. Floating point is a kind of an approximate world in which we restrict our infinite decimals to a specified finite amount and make all our computations there. The standard approach, though, is that we have a theory of infinitesimals. So, for example, we have and maybe another one. Here are two infinitesimals. Let's inquire as to how we do arithmetic with infinitesimals. Let's inquire about this. Okay. This is not something that Steven taught us, because in Steven's situation, the decimals ended at the rightmost point, and therefore you could start on the right-hand side, like we like to do with integer arithmetic. Here the decimals go on indefinitely on the right-hand side, so we are a little bit in a more problematic situation than with Steven. So how are we going to add these two things? Well, we have to start on the left, right? Because it's the only place we can start. So what I'm going to do is I'm going to do this, but I'm going to arm myself with eraser as well. Okay, so let's start on the left. 2 plus 3 is 5. 5 plus 1 is 6. 8 plus 1 is 9. 4 plus 6 is 10. That's 0. I carry the 1. Whoops. Okay, I have to rub that thing off because it's been a carry. And that means I have to rub that one off as well. I have to be prepared to do this. Because that's the way arithmetic works. There's carries coming from the right. Okay. How about here? Here's another 9. It's another possible carry. 1, 2, that's 3. So that means I'm safe about that 9. It's not going to change anymore. Okay, and then 5, and then 9, and then 9, and then 9, and then 9, and then 9. Helps. Okay, so what about this one? Do I know that that's a 5 yet? No, not quite yet. I need a little bit more information. How much more information? Well, maybe the next one will settle the issue. But maybe for some perverse reason, this sequence of 9s carries on for the next 3 light years. Okay. So I take my rocket ship and I just keep on going, and for some strange reason, these two things are all giving me 9s. So what is the algorithm that we are going to teach our young people to actually how we do arithmetic, in addition, in this case just addition, with these infinitesimals? How are we going to tell what our young person should do, in order to actually find out whether that's a 5 or a 6? Should we say, well, you just keep on going until you reach something that's not a 9? The problem with saying that is that it could be that this sequence of 9s perversely carries on to infinity. To infinity. But we just don't know that from this end. Okay, so that's a conundrum. How do we deal with that? Well, obviously we should ask whoever is giving us these sequences, what the pattern is. And we can look at the patterns and determine whether there's some kind of conspiracy here that these two people have just conspired against us, or whether it's just luck. And now we come to a crucial issue, which is the issue of choice versus algorithm. By the way, how many people believe that infinitesimals work? That there are infinitesimals and that there's a reasonable arithmetic with infinitesimals? Yes? No? Okay. All right, so those of you who are confident that there is such a theory, let me ask you a difficult question that Ludwig Wittgenstein, who was the most prominent philosopher of the 20th century, posed to the mathematical community. He said, what are you actually talking about when you talk about infinite processes? Are you talking about things that are given by choice or things that are given by algorithms? When you write something like this with the 3 dots, what are you actually thinking about? Are you thinking that there's an oracle that's sort of just making up these things one at a time, like I've just been doing, rather randomly? Each one perhaps independent of anything that's gone on before? Or are you imagining that there is a computer program or an algorithm or a function or some kind of rule that is generating those sequences? Wittgenstein said that there's a huge difference between these two. And you're not allowed to scurry back and forth between them depending on what's convenient. You have to actually make up your mind. And that the set theorists were not doing that, the analysts not either. So let me ask you to make up your mind now. The infinite decimals that you believe there's a valid arithmetic for, are you talking about decimals which are given by choice, in other words, having some oracle that makes an infinite amount of independent decisions? Or are you thinking about sequences given by algorithms? How about choice? Who believes in choice? Who believes in algorithms? Oh, there's a few not sures. Okay, here's another question. What do you think the status quo out there is? What does the mathematical community believe in? What's the official position of modern pure mathematics? What do you think that the official position is? Do you think it's a position of choice? Do you think it's a position of algorithm?
I think it's C is for choice. The axiom of choice is assumed.
Okay, so that might be. Now I'm just asking what you think is the standard position. So Hendrik is right. The standard position is this one. When a pure mathematician talks about an infinite decimal, that is what they're talking about. That means that if I want to resolve this problem of how to determine whether the sequence of 9s ends or not, I'm not in a position of doing that because there's no algorithms that I can check. I can't look at the code behind these sequences because there is no code. There is no code, and that means that there actually is no algorithm for figuring out whether that thing there is actually a 5 or a 6. Multiplication is even worse. So the problem is, it's not just the problem of the definition of what these objects are, although obviously there's already some difference of opinion, at least quite a bit of difference between these positions. But there's the question of what the operations are, and then how does one actually prove the laws of arithmetic once one has made those choices about what the operations are. It's not enough to define the operations. You still have to prove the distributive law, for example, the commutative law, the associative laws. Has anybody seen a proper write-up of arithmetic with real numbers and read it? Yes? No? Okay. You see that we're starting to get on some kind of dangerous territory here? We all pay lip service to this theory which supposedly is out there, but are we actually in possession of it? Where is that theory? Okay, let's have a little bit of fun. So one excellent exercise for would-be analysts is to try to create such a theory, okay, for things that we do have control over, and those are periodic decimals, or otherwise known as fractions. So if we have a periodic decimal, let's say 0.79 repeated, which is 0.79, 7979, and so on. And suppose I also have 0.857142 repeated, and I want to add them. Okay. So I'm adding 8574142, 8574142, etc. So this is now a more restrictive position, right? Now we don't have to worry quite so much about the phenomena that we had over there because everything is periodic and we have complete control over these sequences. So now it's a very natural question is, if we restrict ourselves to this much more restrictive domain, are we able to create a valid arithmetic? Of course, we could convert these to fractions and do fraction arithmetic, but it's interesting to see if we could actually do the fraction arithmetic in the context of real numbers. That would be sort of an elementary exercise for analysts, right? So, one can do this, and it's not too hard to do. We do the same kind of thing that we did before, armed with our, so there's a 5, and then there's a 4 that becomes a 6, and then there's a 4 that becomes a 5, that's a 0, becomes a a 0, and that becomes a 5. And then there's a 1 that makes that a 1, and then there's that a 1 that makes that a 2, and this one is next to 7, and then there's a 5 that makes that a 2, and then there's something that makes that a 6, and that's where it repeats. Okay, so you end up getting 1.65512 repeated. So now here's a possible program that you could actually try to establish the laws of arithmetic for fractions in the context of real numbers. This is now at least potentially doable. So you could actually write down an algorithm that represents what we did here. I have to be a little bit careful in terms of the periodicity and so on. We could get under control. And then you could attempt to define the operations and actually do check that the laws of arithmetic were satisfied. But I want to show you another much better way of doing this. It goes back to Euler. So Euler do the following remarkable fact, that 1 plus x squared plus x cubed and so on, plus x to the minus 1 plus x to the minus 2 plus and so on equals 0. So Euler said, all right, let's do this in a, well, maybe Euler would not have said this, but here's another way of thinking about making this computation. So we could also make the computation by writing the first thing as point 97979797, a minus sign. This thing here is equal to this thing here by Euler's relation. There's powers of 10, powers of 100, positive as well as negative powers of 100. Okay, and then the other one would be 2, 4, 1, 7, 5, 8, and then repeating 2, 4, 1, so on, with a negative sign. So we're going off to the left because the carries go off to the left. So if we add them at this stage, we get the minus sign, a 1, and then a 2, another 2, another 5, another a 5, and a 6, and then I guess a 2, and then a 2. And if I add a 1 to that side, and I add 1 to that side, I haven't changed anything. And now this thing is periodic, and I see that I'm just getting, I'm not sure if I wrote it down right, 1.65512, there should probably be a 1 here. Repeat. So you can think about it, we can make exactly the same calculation with these sort of reversimals. Actually, the fancy mathematical term is 10-adic arithmetic, really. But it's really an interesting alternative that should be thought about. Okay, so now let's have a look at analysis and some challenges with analysis. Real numbers are problematic because of the definition of real numbers being problematic and the arithmetic, improving laws of arithmetic are difficult. Let's have a look at limits. Okay, here's a sequence. 1, 1/2, 1/2, 1/3. Okay, so sequence. And I'm interested in what the limit of the sequence, called Sn. And I'm interested in what the limit of this sequence is. So in the late 19th century, mathematicians came up with an official definition of what a limit is, which seemed to eliminate the various problems of 17th and 18th century analysis that worried Leibniz, Newton, Euler, and so on. So the definition is that this thing means, I'll remind you, let's see, that for all epsilon greater than 0, there exists an n, a natural number, such that if little n is bigger than n, then the absolute value of Sn minus L is less than epsilon. Does that look right? Okay, familiar definition. So I want to ask you, does this thing make sense? That's my next question. Okay, why? Well, of course, you'll say, of course it makes sense. That's what we learn, and that's what it's in all the textbooks. So why can it not possibly make sense? Because in order to establish this, what is the actual law telling us? It's telling us that for all epsilon greater than 0, there exists a natural number. It means that we have to create a table. We are obliged for every epsilon to find an n. What are the epsilons? Are the epsilons natural numbers or real numbers? They're real numbers, right? Yeah, so what's a real number look like? Well, it looks like 3.59648 ... going off to infinity past the dark end of the universe. Carry on. And that's one epsilon. So you have to find an n for that. Maybe 100 works for that. And then you have to choose another epsilon. Okay, so you have to go through your list of epsilons, and for each one of them, you have to find an n. It's like a lot of work, isn't it? In fact, there's obviously an infinite amount of work here. There's an infinite amount of work that we're being asked to do. You say, wait a minute, in my analysis course, there never was an infinite amount of work. It was just some little formula, like the n turned out to be the 1 over the square root of epsilon or something like that. Why is that? It's because the examples that you were given are all baby examples. They're toy examples. They're not really representative of what's really going on. Okay? They're carefully concocted so that you have this false idea of understanding this concept. The reality is more like this. You have an infinite amount of work to do. And it's not just a countably infinite amount of work. According to Cantor, founder of set theory, these real numbers are not even countable, so this is this larger infinity of real numbers that we're actually dealing with. Let me propose another definition, okay? That an alternative definition, that this definition should really be as follows. That for all m, a natural number, there exists n, a natural number, such that if n is bigger than capital N, then, and I'm going to replace this with Sn minus L squared, I like that better than the absolute value, is less than 1 over m. I'm proposing a new definition of what limit means. So now I'm quantifying over m a natural number. The point is that we don't care about all epsilons. We only really care about a sequence of epsilons going to 0. So why is our definition framed in terms of for all epsilons in the first place, if we're really only interested in a sequence going to 0? This way we quantify only over the natural numbers. It's still an infinite amount of work, but first of all, it's a countably infinite amount of work, and it's organized in a much more logical fashion. How many of you are convinced that this is a superior definition than this one? Yes? No? Okay, now what about this sequence here? So let's apply this definition, whichever one you like, and let's ask, what's the limit of that sequence? You're saying the sequence is undefined, because why? Because we don't know what the pattern is. But we just said that sequences are given by choice, not by algorithms. We're working in a world in which things are determined by choice. Whoever is generating this sequence is not obliged to tell us what the rule is. They're only obliged to keep on spelling out more and more terms of the sequence as much as we want. There's no way we're going to be able to determine the limit, is there? Unless we assume godlike powers. That's a consequence of having this choice aspect built into the situation. Okay, so let me tell you actually what the algorithm is. there's actually an algorithm here. And it's related to a famous unsolved problem, in fact, one of the most interesting unsolved problems in all of mathematics, which is the Collatz conjecture. The Collatz conjecture is that if you have, you start with a number n, a natural number, and if it's odd, you replace it with 3n plus 1, and if it's even, you divide by 2. And you continue, you stop when you get to 1. And the Collatz conjecture is that you always get to 1, no matter what natural number n you start with. So I'm using this Collatz conjecture to generate this. And how am I doing that? Well, I start with the number 1, and it's already 1, so I stop and I go to the next one. So with 2, I'm really going 2, and I'm dividing by 2 to get 1, and that's 1, so I stop and go to the next one. So here I'm starting with 3, and then it's odd, so I go to 10, divide by 2, 3n plus 1, divide by 2, divide by 2, divide by 2, divide by 2, and now I'm at 1, and so I go to the next one. The next one is 4, then I get 2, 1, then I go to the next one. So I'm using the Collatz conjecture to generate a sequence, and this is purely computational thing. You could write a little one-page code that generates this sequence. So now we've moved into the much more habitable arena of algorithmic sequences, where we have at least some control over things. So let's ask the question, what's the limit? And are we able to prove that the limit is what it is? Well, the limit is probably 0. It's 0 precisely when the Collatz conjecture is true. So if you can determine that this limit is 0, you've basically solved one of the most famous problems in mathematics. Okay, so what about suppose I tell you that the limit actually is 0. We get some oracle. How are we going to actually go through the motions and use this definition to verify that? So even if we do this one, so suppose we know that this goes to 0, but we want to find out for every epsilon how far you have to go before you get to epsilon. You still need to know something about the Collatz sequence and what kind of bound you have on how long it takes to get to 1. We don't have such information. So it's impossible to use this definition to talk meaningfully about the limit in this situation, unless we solve some famous problem in mathematics. The very definition of limit is, in fact, highly difficult. Okay, what about another? Important weakness. So let me introduce a topic which is very important in algebra and undergraduate mathematics, which is the fundamental conjecture of algebra. It's related to the fundamental theorem of algebra, which is, however, unfortunately not really a theorem. Okay. So why is the fundamental theorem of algebra not really a theorem? Well, it's because if you actually have a polynomial and you ask your computer to find a 0, you can try this yourself. If the polynomial is reasonably big and you ask it for a 0, it's not able to do it. What it is able to do is give you an approximate 0. In order to find an exact 0, you have to basically do something like Stedman did. You have to set up some process, and then you have to run that process to infinity. You have to complete an infinite number of work units. Only then, at the end of that infinite process, do you actually get a 0. We're not able to do that, so that it's not really a theorem. And that's why the proofs of this thing have been so elusive, because it's not really set up in the right way. So I want to show you a correct version of this thing, which is, however, not a theorem, it's a conjecture. Okay? And it should be a very famous conjecture, because it's a crucial result. Okay. So here is the a correct statement of the result. All right, so given a polynomial, say P of Z, with complex rational coefficients, and a number, say M, natural number, there exists a Z in C, let me say C rat, to denote a rational number, complex number with rational coefficients, such that the quadrants of P of Z is less than 1 over M, where the quadrants of A plus BI is A squared plus B squared. So this is a purely rational form. If, as I do, you do not believe in real numbers, you can understand the meaning and the content of this theorem. It's purely in terms of rational. You have a polynomial with rational coefficients. You're looking for a complex number with rational coefficients so that when you plug it into there, you're going to get a complex number whose size, as measured in this algebraic way, is less than some predetermined 1 over m. So it's a remarkable fact that this is true. By the way, this is not the strongest form of the fundamental theorem, but it's a form. And this is in need of a proof. All the proofs that we currently have use continuity arguments or topological arguments, which in fact are not substantiated by our current technology, which assume various convenient things about real numbers. Why do we want real numbers so badly? It's because real numbers give us. They give us lengths. A curve really has a length, and that's an exact length, not just an approximate length like our computer is telling us. A region has an area. There's a region. It has an exact area, not just an approximate area like our computers are telling us. Values of functions. For example, cosine of phi. It's an exact value, not just something approximate like your computer is telling you. Solutions of equations. Eigenvalues. So the list goes on. There's a huge number of things that we want our real numbers for. Our real numbers, unfortunately, don't have a solid enough foundation. And this was, well, this was really the reason why set theory was really instituted in order to try to buttress real numbers. So Dedekind had a form of real numbers that involved infinite sets, as did the Cauchy sequences of Cantor. And this required some kind of set theory. And so that's basically why we've given the set theorists sort of a blank check to create whatever axiomatic system they want, as long as it works to give us our notion of sets, which we need for our real numbers. There are lots of problems with modern set theory in terms of the definition. So modern set theory basically avoids the problem of whether we actually have to say what a set is. So set theory, of course, collapsed early in the 20th century due to these paradoxes. And people had a hard time resuscitating it. And so what ended up happening was that we retreated to an axiomatic position. The axiomatic position is that there is a theory of sets, but we don't actually have to say what a set is. That's the problematic thing, not saying exactly what a set is. But with this axiomatic position, we just get to say what the properties are. So this is a theory that collapsed around the year 1900. Mathematicians were not able to resuscitate it. And then several decades, well, shortly afterwards, people came up with this basically list of so-called axioms, which are supposed to be self-evidently true. and which notably do not start by defining these various words. So there's no definition of set, there's no definition of property, of parameter, of elements, of union, of subsets, of infinite set, of function, of family. All these terms, but there's no corresponding definition. You're just supposed to have an intuitive understanding of what these words mean. And in particular, I'd like to note the axiom of infinity, that there exists an infinite set. That's a self-evident axiom.
Yes.
And how about this one here? This is the crucial one that we've seen already. Choice. Every family of non-empty sets has a choice function. The real reason for this thing is not to prop up topological vector spaces and Zorn's lemma and so on. The real reason is to prop up the theory of real numbers as infinite decimals that you don't have to specify algorithms to talk about. That's the critical issue there. Because if we had to talk about algorithms, we would have to learn about the theory of algorithms. And that's a whole ball game that we don't want to go down. And so we retreat to this axiomatic position, and it's all a little bit unfortunate in my opinion. Okay, so there's a lot more to say. If you're interested in this line of thought, I have a series, Math Foundation series on my YouTube channel, which goes into all of these things at great length. And I thank you for your attention and your participation. Thank you very much.